All right, I think we're ready to get started here. Oh, that was like fingernails on a chalkboard. Um, Thank you all for coming. Tonight, as you know, we have our Steam Cafe event here every month, and it's not possible without the partnership of South Dakota Public Broadcasting and Hay Camp Brewing as well. And it also wouldn't be possible without all of you attending. So thank you all for being here. And to start us off tonight, I'd like to introduce our speaker. Dr. Jon Kellar is a professor in the Department of Materials and Metallurgical Engineering at South Dakota Mines. So I will turn it over to Dr. Kellar.
Great. Thank you all for coming. It's a great time to be right between the semesters start. So thank you all for coming. This is a talk I gave last spring on campus, and it's really focused on Smelter Hill. I grew up just a couple blocks from campus, and so I have a lot of fond memories from the hill. And so we're going to look at it in a little different perspective from normally, hopefully. And so there's 4 case studies I'm going to go through where we worked with students on different projects associated with Smelter Hill. But before we do that, I thought it'd be good to take a little historical perspective of the school itself and how it got situated where it is next to the hill. Um, we started out in Dakota Territory. Um, prior to 1874, the Black Hills were within Dakota Territory, but the federal government wouldn't allow people into the Black Hills. And in 1874, Custer, of course, led an expedition into the Black Hills. And you can see this in the picture on the right, an encampment about 1 mile east of Bluebell Lodge there. If you go to Custer today, I was at Sage Creek Grill, and they've got all these pictures of that Custer's expedition took in 1874 and then current day. It's really interesting. Most of the pictures show that location where the encampment was and where they took the picture at the time really haven't changed a whole lot. Um, but of course, that same year, gold was discovered on French Creek. Custer still has gold discovery days during the summer. That caused the famous gold rush, and prospectors moved into the Black Hills, even though it was off limits, according to the federal government. Rapid City was called Hay Camp. So we're at Hay Camp Brewery. That's pretty cool. And the city was first plotted in 1876, which is roughly where Dakota Point Brewery is today. And that's, of course, why we call the across the street Founders Park. But it wasn't until 1877 that the federal government opened up the Black Hills. So clearly there was a lot of activity not authorized by the federal government happening in those years between when Custer came and 1877. And then just as a side note, oops, go back here. 3 horse thieves were hanged on a tree just north of present Dinosaur Park. And I think the remnants of that tree is still there. That was also 1877. 1883, a bill was to create the School of Mines, passed the legislature, but it was vetoed by territorial governor Ordway. So that was we were still a Dakota Territory. And then there was a lot of debate if a school was formed, would it be in Deadwood? Would it be in Rapid City? And then finally, $10,000 was allocated to establish the Dakota School of Mines in Rapid City in 1885. So we see today merch in the bookstore established 1885. So a tremendous amount of activity happened between 1874 and 1885. Just a remarkable amount of activity, and it led then in 1885 to the school, and it was sited where it is today. The first building was that prep building shown here. It was torn down in 1972, which was the same year as the flood, but it wasn't torn down because of the flood. It was just, its time had come. And then statehood occurred in 1889, and then we became the South Dakota School of Mines. So a tremendous amount of activity there associated with the formation of the school and the Black Hills. There was a gold chlorination plant built just above present-day O'Hara Stadium in 1891. You can see the picture there of that chlorination plant. It didn't last very long. And then in 1901, the National Smelting Company built a smelter on top of the hill. And that's shown here, present-day Smelter Hill. There was a smelter along, I think, pretty close to one of the ramps in present-day football field. I'll come back to this starred location here in a little bit. But that smelter existed between 1901 to 1920. It wasn't profitable. It was never profitable, so it didn't last long. And this date I've had to talk to a lot of people about. It might be a little bit fuzzy, but 1955 students detonated the base of the smelter during a graduation ceremony that was happening at O'Hara Stadium. And then the remnants of the base of that smelter are used today by the Greeks on campus, and I'll show you some of that later. So that's kind of, we had the formation of the school, the smelter adjacent it, and then it becomes later what we call Smelter Hill. Now we're going to go way back in time, and I'm very dangerous here. I've got geologists in the audience, so I have to be careful. But during the late Cretaceous period, we're talking 100 million to 66 million years ago, there was a large interior seaway over present-day South Dakota. So we were in the middle of this seaway that came down through present-day United States. Its widest expanse is about 620 miles wide, about 2,600 to 3,000 feet deep. So it was pretty massive. There was a lot of volcanic activity and periods because of the volcanoes, a lack of oxygen in that inland seaway. The sediments left are referred to as Belfouche Shale, or as my children say, Belle Fourche. Belfouche Shale. Sometimes it's also called Granero Shale. And then after that, the Black Hills uplift occurred, and in that process exposed this shale that had been deposited in the seaway. And it's roughly about 250 feet deep, this Belfouche Shale. So where is it? This is a portion of one of the maps on the third floor, the geology quadrangle around Rapid City. Case B in that map is Belfouche Shale. You can see it's described as shale, dark gray to black, plastic, clayey, and it contains bentonite partings. You can read the rest. So here's the school. Here's the track. This red dot is approximately right here. You can see the windmill that never turns that we have on the school. And this exposed area here is this Belfouche Shale on the southern exposure on Smelter Hill. And Michael, if you could grab that bag of Belfouche Shale there, so you can get a sense of what we're dealing with here. It's really interesting material in a lot of respects. It's also kind of nasty in a lot of other respects. So here it is. This is what's in the bag. Large plates of this shale that were compressed when it was in this inland seaway. How do you define shale? Clay in the form of small compressed flakes oriented at right angles to to pressure producing a cleavage. So it fits the definition. But what caught my attention was that word clay, because we've been working over the last now 4 or 5 years, looking at local materials for artistic purposes. And so that caught our attention. We ran X-ray diffraction, which is just an analytical technique that tells us that it is 42% montmorillonite, 39% quartz, 9% muscovite, and then kaolin clay. And from a ceramics perspective, that isn't bad. You need, to make ceramics, you generally need quartz and clay. Now we'll see that this particular mixture isn't ideal, and we're going to have to do some processing. But we comminuted it, ground it in a hammer mill down to a very fine size fraction. So we took that material and ground it very, very fine, roughly down to the diameter of the human hair. So it's a powder at this point. We did some particle size analysis, looked at it in the scanning electron microscope. We've got incredible facilities in the mineral industries building, including a scanning electron microscope. And we could, oops, go back here. We could see some plates of clay, which from a potter's perspective, you need those clay plates so that the clay will slip by your hands when you're forming a pot. So it's kind of nice from that perspective. Very, very fine particle size. So when these sediments were being deposited, very, very small particles of quartz and clays were present. Why do we care? Like I said, we care because we're interested in ceramics. Prior to about 1900, most of the building structures in Rapid City and the Black Hills were made from local clay-based minerals. So we made bricks. A lot of the bricks came from around Belle Fourche, but after about 1900, we went to stick-built lumber. The largest brick company now near us is in Hebron, North Dakota. So we're still importing a lot of our bricks from North Dakota, but we've got a lot of those minerals present if we ever wanted to get back in the brick making business. So I was interested in Belle Fourche shale for those sort of applications. And specifically, the problem with Belle Fourche shale was that of drying. So we go through the process for ceramics. We form it into using a mold or a wheel or whatever forming process while it's kind of a wet slurry. We let it dry, and it's during that drying process that cracking can occur. But if it doesn't occur, we fire it in a kiln and to get the final ceramic. And it's this so-called green body. I don't know why they call it green. There's nothing green about it. It's basically dried ceramic. You have to dry it before you fire it, and you want to avoid the cracking that occurs as the water evaporates out. So with this Belle Fourche shale, we found that this montmorillonite, it's called a smectite clay. It is the same clay that's the active ingredient in kitty litter. It absorbs a lot of water and will crack with a ceramic. So it's good from a chemical perspective, but it's bad from a drying perspective. It's not the most ideal clay. That was a problem, and it causes great shrinkage. A normal clay may shrink 10% with kaolin, the desired clay, but in our case, it might shrink 33%, which is just a tremendous amount of shrinking, lead to cracking. So how could we use this material and minimize that cracking was kind of the question. And there's two approaches we took. One is more chemical, and one is more structural, and we'll go through how we approached those. So In terms of processing, we would take this ground Belfou shale, add the water, mix it in what's called a thinky mixer to produce a slurry of the material. And then we would take that slurry and put it into a ceramic mold here. This is a coaster mold, so it's made of plaster of Paris to facilitate the drying of the Belfou shale slurry. You can see the size, it's about 4 inches by 4 inches and about half an inch deep. And then we would dry it at a fixed relative humidity for 12 hours. And this was kind of the setup. You can see it's an enclosed chamber. Here's our sample. And then we control the humidity at over 12-hour time. And we kept the relative humidity between 45 and 55%, just to keep a constant relative humidity in our test chamber, in our drying chamber. And this is what the sort of behavior that we'd see: 30% water after 12 hours, a little cracking, 40% water, a lot of cracking, 48% water, just a tremendous amount of cracking. And the cracking is bad because we want to form the piece, let it dry, and then put it in a kiln and fire it. So cracking is bad. And we saw that right away with this 30% water content. So the first approach was to add polyacrylamide. We'll call it PAM. It's a water-soluble polymer. The civil engineers use PAM for stabilizing clay-based structures. And so I thought it'd be worth trying here. So we had to grind it up a little bit, and we added about 0.5 weight% PAM to the system. You can see it was very sticky by nature. And so that was the chemical approach. The structural approach was to add 1% tissue paper. And I don't think Jacob Peterson's here, but this was his idea. And so we literally went to the bathroom, took toilet paper, shredded it up, and added 1% tissue paper in the form of cellulose. Here's the chemical building block of cellulose. And here's in a crack that we did produce, you can see those cellulose fibers at least trying to bridge the crack, so it gives it some structural support. And like I said, we used 1% tissue paper to help give structure. And as it turns out, it slows down that drying pretty significantly. And so here's some results: 40% water only, a lot of cracking; 40% water with the tissue paper, no cracking. Right? So the tissue paper gave both the structure and also reduced the drying very significantly, no cracking. 0.5% PAM, no cracking. And of course, we had the combination of PAM and 1% paper, no cracking again. The problem with the PAM, though, it was so sticky. It was hard to work with the piece, whereas the tissue paper actually caused the material to have the feel of a normal clay, a kaolin-based clay. So it was really nice to work with. So we focused our attention then on the cellulose addition. So what are the limits? Well, the limit is we could add about 40% water and have no cracking if we had 1% tissue paper added to the system. So that was a really nice amendment to the Belfou shale to allow us to use it as a ceramic with no cracking. And so what happens when you fire that material after it's dried? You can see it turns kind of this orange. This is 40% water, 1% tissue paper, and then the PAM additions here. But there was still no cracking even after we fired it. And Michael, if you could grab these two pieces here. One of them is Belfou shale that a student, Baylor Larson, uh, printed, 3D printed, and you'll know the difference between these two. One is 3D printed, and the other is one of Dr. Donovan's high school teachers who was working with her 2 summers ago was a great potter, and she threw that pot with this Belfou shale with this amendment. And so when you fire Belfou shale, it turns that orangish color. The iron oxide oxidizes, and then you can get different shades of either orange or red depending upon how high you go with the kiln. So that was a success. We were able to take this really difficult to work with shale that we pulled off the back of the Smelter Hill and amended a little bit, and either can do 3D printing. We made a lot of bricks with it also, or throw it as a pot. So it's a success story, I guess. What about performance? We looked at 3D bend strength. Really, the paper actually increased the strength a little bit. Now you're saying, well, after you fire it at 1,000 degrees Celsius, the paper's not there, right? It's either a char or something. It's decomposed, and we'll come to that here in a minute. But in terms of strength and performance, the amendment with the tissue paper also increases strength a little bit. So for all purposes, formability, strength, that amendment, very low cost. We published this paper on this, and I had to go to Geraldine Roberts and say, can you give me the vendor of the tissue paper in the bathrooms? And she says, why? I said, well, we have to say where we got our tissue paper. And so very low cost addition to a low cost material, because we just dug it out of the side of Smelter Hill. We also did some micro-computed tomography. There's some nice images showing that the voids where those cellulose fibers were after firing, they're probably tar or some decomposition happened. You can see in these 3D renderings from a micro-computed tomography. So we're going to shift gears a lot. We're going to stay with Belfou shale, but our interests are going to shift dramatically. Last summer, I had a student, Austin Helgert, who was interested in an undergraduate research experience. And I love walking around in the Mineral Industries building. And if I find Bill Rogenthien, I just really enjoy talking to him. And I don't know how we started talking about micrometeorites. Oh, I do know, because Michael West had a high school student from Stevens High School, and their physics teacher was having them go on rooftops and collect sediments from rooftops looking for micrometeorites. And so I happened to be talking with Bill Rogenthien, and we kind of hatched this idea of, could we find micrometeorites that had fallen into Belfou shale during the time of the Great Uplift, or before the Great Uplift, 60 to 100 million years ago. And so we went. Micrometeorites are falling continuously. And what are they? They're just really small meteorites, less than 400 microns in size, typically, and they're divided into very different categories of micrometeorites. I've highlighted in red down below in the middle section. A lot of them contain iron and nickel. And so those are two very strongly attracted to a magnet, have high magnetic susceptibility, which caused us to think that maybe we could concentrate them magnetically. Um, and off we go. This is a summary table of micrometeorites that people have reported in different locations. A lot of them are deep sea environments, or they'll be in sands. A lot of them come from ice in Antarctic or the Arctic, where they melt away the ice and look for the micrometeorites. You can see the size. They're quite variable in size, but most of them are pretty small. Um, so typically from minerals, and this is what Dr. Rogenthien actually had done, was they would digest the minerals with an acid, and what's left not dissolved by the acid they would consider as potential micrometeorites. And they're typically spherical because of the way nature in which they fall to Earth. So off we went, wondering, could we find micrometeorites in Belfouche Shale? And so this is a little flow chart we made up, where we start with the Belfouche Shale, we comminute it, we exfoliate it, in that case in a Peter Pugger clay exfoliator, just trying to break up the shale as best we could. We'd agitate it, and then we'd go to WIMS, which is wet high intensity magnetic separation. So we basically take a lot of water and form a slurry of individual particles of the shale, and then run them through a wet high intensity magnetic separator, because the vast majority of the shale is non-magnetic. We were trying to capture the magnetic portion, and then from that start to look for potential micrometeorites. So it was a lot of work, not by me, but by the student Austin. For example, he started in one of the trials. He started with 226.4 kilograms of shale, and after processing, got it down to 5.5 grams of material. So it was 0.021% magnetic. So we got rid of all the non-magnetic stuff by this processing. And then he would take the magnetic and start looking under the optical microscope at the particles. And so he was looking for spherical particles. And one day he thought he found one, and then tried to remove it and lost it. And so he was really sad the first day that he lost it. But you can see pretty clearly in this image that there's something unique about that particle in relationship to the other. So Austin got very good at identifying and removing the particles very carefully that he thought might be spherical and might be micrometeorites. The majority of the magnetic portion here in these samples were either magnetite, iron oxide, or jarosite. The orangish colored ones tended to be jarosite. But nonetheless, we had a lot of fun looking for micrometeorites. That particle that I showed in the previous image is highlighted here, and now we're looking at it under the scanning electron microscope. It's odd looking, right? That was my first conclusion. There's platelets. It looks like platelets, but it's very spherical. We then went to energy dispersive X-ray spectroscopy, which will give us elemental composition. We see it's about 50 atomic percent iron, about 50 atomic percent oxygen, which could be what's called woostite, and woostite doesn't generally occur in these sort of deposits. It's an odd duck, which gave us hope that maybe it's a micrometeorite. So we focused a lot of our attention then on this so-called alpha particle. We have a nice focused ion beam where we can actually cut the particle in half, where they sliced this this, I think it was about 20 micron diameter particle. We slice it in half, and there was a hole in it. The hole, does that mean it's a micrometeorite? No. Does it mean it's not? No, because there's some of them do have holes like that. We found that between the plates, a large amount of silicon, uh, material grain boundary as quartz. Uh, does any of this prove that it's a micrometeorite? No. But it's odd. It's odd. Here's some other candidates. Now he was labeling them Belfou Shale prospect ID number. Once again, this one is an odd looking sphere. And what caught our attention is it does have some nickel in it. Nickel is a very strong indicator of potential micrometeorite. Prospect ID B8P2, it had this strange grid-like pattern. And when we looked at that after fibbing, very interesting dendritic microstructure. And some of these microstructures could be created by this rapid cooling as the micrometeorite falls into this interior seaway 60 to 100 million years ago. So we were convincing ourselves that we're seeing micrometeorites, getting very excited. But there's some voices of reason in the building, Ed Duke being one of them, because he gets a lot of people saying, I found a meteorite, and they didn't. So, and here's some imposters that we found. This is a titanium nickel particle that was found during our processing. And we were getting very excited about this, and Ed saying titanium isn't part of micrometeorites. This is not a micrometeorite. Well, as it turned out, colleagues, Dr. Thompson, Dr. Crawford, had published a study using these nickel titanium particles that somehow had contaminated part of our lab. Yeah, Kelly's like, shh. Yeah. So yeah, we found the culprits, and it's us, right? So that was a little bit humbling, I guess you could say. That was an imposter, and there were some other imposters we found also from people that had done processing in the lab that were tungsten carbide particles. But then there may be these volcano particles. This had the right composition. Recall that during that time of the Great Interior Seaway, there were volcanoes going off. Maybe we found some volcanic particles in addition to some of the alpha particle and some of the other ones that I've shown you. So that's the second case study. These last two will go rather quickly. Of course, there was gold smelting on the hill. Recall that red dot that I showed where the original smelter was. That's roughly this spot above O'Hara Stadium. There's still remnants of a shack from the smelter there. And so in 2015, I told the sophomores we're gonna have a capstone project. Go see if you can find gold up in those remnants. And all of the teams found some gold. Not a lot, but they were able to do the mineral processing and gravity concentration. And they found some gold. And we've repeated that a couple times. So in those sediments, there's some gold you can find. But that was a good start in 2015 because I figured out we could do a capstone project where you turn the students loose, ask them to concentrate different particles. And since then, we've worked with a lot of companies, Pete Lean and Sons, Dynamic Life Cycle Innovation, OMAX, and we worked with the AMP lab who contaminated the lab, actually, right? That's some of those particles that we found that we thought were micrometeorites. So that's been a lot of fun, but it started with these sediments up on Smelter Hill that were left by the smelter. And the fourth example, like I said, I grew up just a couple blocks from campus and spent a lot of time wandering around those hills. And I remember picking berries up there as a kid and bringing them, and my mother would make sand cherry jelly. And so I was always asking, Larry's here, where is he? I was always trying to get it. Can you tell me where the berries are up there? And he's very, very cagey about his berries. But I found them up there, and then, oops, sorry. My mother's 94. She helped me can some sand cherries from Smelter Hill. Not this spring. There's nothing up there this spring. It's been so dry until yesterday and the day before. But so there's no berries up there, Larry, this year. But there were 2 years ago, and we did some canning. Of course, you can access the trail now through Rocker Trail that goes around. It's really nice. We got a grant from Game Fish and Parks to put a trail up there, which is really nice for accessing the berries, some flowers. I picked some flowers for my mother. And, you know, I brought him to her and she said, you can't just go up there and pick flowers. I said, why can't you? She said, well, they're not yours. Well, so anyway, I did, and I brought, but then the other thing I found while we were building the trail is some asparagus, wild asparagus, and that's 2 years ago. It's great, and I will not tell Larry where that's at. So there's not going to be any divulging of my asparagus patch. So some conclusions, we've done a lot of processing with the shale. That Rocker Trail gives us a lot of opportunities to explore that area. So that's my story of Smelter Hill. A lot of people to thank, the students, my mother, Larry Simonson, Bill Roggenthien, on and on. But the research piece, really, it came from an RE, what we call an REU site. Michael West is the lead, and he'll give me a student and take a wild idea and let me run with it. So special thanks to Michael for that. So some references. Thank you. Happy to answer any questions. We still have them. But we haven't published that because you better be darn sure they're micrometeorites before you publish it, or people will tear. It's a vicious thing. That community. So we need to do a little more work to convince ourselves whether or not they're micrometeorites. But we've got great tools to look at them. That's for sure. Yes, Travis.
Flow diagram, add the water and then add that the clay body, or did you add it?
We added it to the water to get it solubilized, and then and then into made a slurry out of it from there. That was a bad first attempt. Before we realized we have to do exactly that, you have to add it to the water. And you know, the PAM worked okay, but it was sticky. And if you're processing dirt and you hope to make a product, the PAM would really probably kill you cost-wise. So we kind of abandoned that and went with the tissue paper pretty quickly. Michael. Yeah, other than it's really cool, right? You know, I think it would help with understanding the geologic record. I mean, if they survived under those conditions, that might help explain the conditions of the interior seaway. How am I doing? I mean, they're ancient travelers from the past, and they may tell you a story about their condition when they came in terms of the, planetary perspective, and then if they survived, how they survived in that particular environment. Yeah, well, Bill Roggenthien was working, I think in his graduate study on a place in Europe where they think the Big Bang happened, the big meteorite that, changed the end of the dinosaurs or whatever happened. And in that case, if I remember right, there was a enrichment of iridium or some crazy element to help indicate that they found the location where the meteor had hit. But cat. Yeah, I don't know. I don't know. We've proven we can process it into ceramics. We can make bricks out of it. Um, I just I just don't know what's what's left to do with it. Um, and until we start making ceramics again, either bricks or other, I don't know. Yes. Yeah. I think there is a lot of potential to go through. There's, I focused on Belfast Shale, but there's a lot of strata. I don't know if that's the right word, caused by the Black Hills uplift. Dr. Donovan's doing a lot with what's called Fuson Shale for processing into ceramics. That's a potential source of micrometeorites as well. I think the nice thing, though, about Belfast Shale is that it was so easily torn apart in water and able to be, that magnetic fraction was so small that made it very amenable to doing what we did, where some of these other layers may not be that easily processed to look for the micrometeorites. That makes sense. Yeah, and we have gone a little bit into the Pierce Shale and looked at that for not for micrometeorites, but more for these ceramic type applications. Um, Definitely. Near as I can tell, I have a difficult time differentiating between Belfast Shale and Pierce Shale in terms of its makeup and how it behaves. They're pretty similar. And then there's the Mowry and Hell Creek, and to me they all look the same and act the same, but they're obviously different to you all. Hey, Travis. That's a great question. We had a high school student through your program and Kat's program make bricks and with and without tissue paper, and then we ran out of time and we never did the testing. But then this summer, the student came back to work as an undergraduate, and she said, "You've never tested my bricks." And so we've got them. We just need to do that because we made them. We've gone on to testing bricks of different type other than those, but we definitely could do it. The civil engineers have been great about letting us do the testing in their facilities. Yes. Mm-hmm. Right. No, that's a good point. So we found the contaminants early in Austin's work, and then we bought all new sieves, all new processing equipment, and that were pristine. And we proceeded, and then we didn't see those sort of imposters anymore. But that it took pretty, by our standards, pretty rigorous cleanliness and new equipment to make sure we weren't going to find those imposters again. Brett? Yeah, we would dig deep enough where we were convincing ourselves that we would get rid of any man-made material. And as you go deeper, you'll encounter these orange materials, which I think are probably manganese or iron or something, which are most likely critters or something uh, that weren't part of the original shale. Well, they are now, but they weren't then. But yeah, I could definitely see these regions with different colors. Yes, Travis. That's a good question. I think I know part of the history. And we did find the material or remnants of the material. It's just outside of Belfouche on the right-hand side of the road. You can see where the workings were, and it's a white clay-based material that's really good for making bricks. And I think they had I think it was called the Black Hills Brick Company until about 1957. They were producing a lot of bricks. Supposedly, they produced the bricks for a Belfouche high school. Um, and I think they were bought by now Hebron Brick, which is in Hebron, North Dakota, and shut down. And that's pretty sketchy, but that's near as I can tell the history. But yeah, they were producing a lot of bricks there in the 40s and 50s. Um, yes. Yeah, we we did do some experiments of using Belfouche shale as cat litter. One of my graduate students took it home and tried it with his cat. It didn't work very well. Um, the he, his girlfriend was out of town when he did it, and it was her cat. But So is it just a little bit risky experiment, but it didn't clump as well as normal kitty litter. And it's because you're about 40% montmorillonite, whereas the bentonite that comes from up around Belfouche colony there is essentially 100% bentonite. So it's not going to be a good kitty litter. And I think it, it, yeah, I don't know. I don't know its potential use. Yes, Colin. Yes. Every once in a while, but they're pretty thin. They're pretty thin. Yeah. Yeah, that'd be good cat litter. But yeah, those were pretty thin. But it's pretty rich in manganese. You know, you're not going to process it for manganese. There's not enough of it there, but there is a fair amount of manganese in there. And then of course there's iron, because that's what leads to the orange pot after you fire it. It's the iron oxide coming out. Yes, Parker.
You know, that clay that we fried from the pot, this painful pottery experience. What part of the process?
That was before we started adding the tissue paper. Yeah, because no, and I tried to teach myself how to throw a pot with this Belfouche shale, and it's horrible. It's really hard to, yeah. But once we got the processing and added the 1% tissue paper, it got very manageable. And I should make some and give it to you. You would appreciate it. You could do, yeah. Well, thank you all for coming, and appreciate your time.
Yes, thank you all for coming. As most of you probably know, we do this every third Tuesday of the month at 6 p.m. And so our next one will be September 15th. And we're still finalizing the details of the speaker, but it will be a guest speakers being sponsored by the Humanities, Arts, and Social Sciences Department. So we'll have an off-campus person presenting next month. So you all come then. Thank you all for coming.